Um, so yeah, it's called the quest for the fastest deployment time, and I'm gonna talk to you about the time it takes between you making a code change and that change being live on your development cluster. Um, so caveats. I am never awake this early in the morning. So if I sound drunk, it's just my natural drunkenness. I swear I didn't consume any substances, okay? Um, so let's get to it. Like Natalie said, I work at Tilt, and it's one of the very few companies focused on the development experience side of Kubernetes. And basically, the most important metric in terms of developer satisfaction is how fast is it between you making a code change and that change reflecting being live and working. So it's a fast feedback loop. That's what really matters. And see, I'm sleepy, so I'm losing my train of thought. The other thing that's important is to not have to do a bunch of commands to update things when you make a change, but we're not going to deal with that here. And also, we're not going to have to type in commands, so that's great. So yeah, having a short feedback loop is super important, and Kubernetes makes it really hard. So we're going to fix it. And my promise to you is that, so let me show you what this is. In November, I asked people on Twitter, and almost 2,000 people voted. Well, 1,000 because half of them didn't really vote. And they said, like, how long does it take between changing a line of code and that change being live? And most people said 30 minutes, and I think that is really, really sad. A lot of people said 1 minute, and that is not terrible, but 1 minute is enough time to pick up your phone, look up, social media, blah, blah, blah. And then you get distracted from your code. You get distracted from what you're actually trying to do. And I find it important to have that interval be very short so that you change your code and you alt tab and such, and then, oh, there you go, here's my stuff. And you don't lose focus. You're always on one train of thought. So like I think psychologists call it like the flow. So you're always in the flow, and I think that's really important. So depending on what you're doing, of course, you're not going to be able to have a 2 seconds of feedback loop, but you're going to be able to have something around that order of magnitude. Um, I'm going to show you how to make it under 2 seconds. So let's get to it. So what do we need? What are the important things for having such a short feedback time? So the first one is sometimes for some things, it's really important to have your development environment very closely reflect your production environment. For some things, it makes zero sense. So for example, you probably do want that the code you run in development be the same code you're running in production. You probably do want your images, your container images to be the same in development as they are in production. CI, though, makes zero sense and it takes forever. So here's what you do. When you're developing, when you're iterating, you do that on a simple and very fast feedback loop. After you're like, okay, this works, I'm happy, I'm gonna push a PR, then you do CI. So this sounds really basic, but lots of people they're like, oh yeah, I changed the comma here. Now I need to wait half an hour for CI. And I don't think that makes sense at all. And none of the people who are doing development experience right do that either. Okay, number two, you should use an automation tool. So if people are talking, Docker build, Docker push, kubectl apply every time they change a comma in their code, you're losing time and you're getting distracted, and that just feels frustrating and sluggish for everyone. So use an automation tool. So I coined this what's the word in English when it's a bunch of little letters, acronym. So I coined this acronym MDX. It stands for Multi-Service Development Experience Tool. And there's a bunch of MDX tooling out there. So there's the one I'm going to present to you, and that's Tilt. There's Scaffold, made by Google. There's Telepresence by DataWire. There's Garden, where I used to work. So there's a bunch of tools in this realm. I'm going to show you Tilt because it's the tool that is closest for me. But other tools can work as well, depending on what you're doing. Every tool is a bit different, but I'm just saying it's not like, oh, you have to use my tool, so because that would be weird. Third thing is absolutely use every little hack and cheat and dirty trick in the book to make feedback loop smaller, because Every little bit counts, and every second that you make the feedback loop smaller is going to make developers happier. So that's really important. And I just realized I don't have a timer here, so I don't know how fast or slow I should be. Do I have a watch? I don't. So let's just play by ear. Okay, so the goal of this talk is to show you how to achieve a very short feedback loop for a Go application. And here's how we're going to do it. It's a Go app. It has a few microservices. It's going to run in Kubernetes, and everything I'm going to show it to you is going to be benchmarked twice. One running on a local cluster on my laptop, and that's going to be microkate. You can use Kind, you can use Minikube, you can use anything you want. I'm using microkate because it's already installed. And in parallel to that, we're going to use GCP, Google Cloud. So we're going to have both an example of local development and remote development. So you're able to compare the two and see maybe whatever works best in your case. It's all going to be working with Tilt, like I mentioned. And I'm going to use very precise benchmarks because I am annoying like that. So we're not going to do anything, oh, this feels faster. No, we're going to count it down to the millisecond. So this is the app I'm going to show you. It does image filtering. So here's a red filter that turns an image red. Here's a glitch filter that adds some glitching to my image. And we didn't have a front end back when I recorded this. This was a very early version of the app. If you look at this app right now, it's really pretty. I'm going to make a video showing this app in a few days. So I'm really excited about the example app, but you probably don't care about that. So the last filter, it just uses machine learning, and it adds labels. So the baby there is a person and the teddy bear is a teddy bear. But we're just going to focus on the glitch service. So it's the one that made the whole picture ugly, basically. So we're going to focus on the glitch service. We're going to simulate making changes to the code there, and we're going to see how long it takes between a change in the source code and the new code being running. So that's what we're benchmarking. So Tilt's going to watch for code changes. Whenever a change happens, it's going to do the whole rebuild, redeploy, update thing. And we're always going to benchmark from the second build onwards, because when you deploy an app for the first time, there's a bunch of stuff that needs to happen, and it doesn't happen afterwards. And if you spend 3 hours writing code, you only do the first deploy once, and you do the second deploy 100 billion times. So that's what we're focusing on. By the way, this talk used to be presented in a much longer time, and I'm going very fast here. So if something doesn't make sense, if you have any questions, please reach out on Twitter. I'm not sure how much time we're going to have at the end. So just tweet away your questions, and I'll get to it afterwards. Okay, so disclaimer. This talk is not a Tilt tutorial. It's not going to teach you how to use Tilt. And some things I'm going to do are even things we absolutely recommend against doing. So don't take this as gospel for Tilt. So if you're interested in Tilt, check out tilt.dev and come talk to me later, and we can go about that. But in this talk, it's not going to be Tilt focused. It's going to be focused on Go and Kubernetes. So let's get started. I'm going to first deploy my glitch service in the absolute simplest way I can. So here's a very simple Docker image. I'm using a Golang Alpine image. I'm copying a bunch of files there, and I'm going to compile, and then I'm going to run my compilation artifact, and that's how everything's going to work. The tilt file is what tells Tilt, hey, this is how this service works. So for this example, we're not using all the services in the app. We're using just 3. So I have first, how do I get the laser pointer here? Yeah, so we have a Docker build thing, Docker build function that's going to build all the images. We have a KTML function that's going to say, okay, here's how we run these images, basically. This Kate's resource is just adding a port forward to my Muxer so that I can access it from localhost, from outside the cluster. And the local resource, this is a function that lets you run arbitrary commands, basically. So if Tilt doesn't do something, you can just do it by yourself with a local resource. And this is very complicated. So here's what this does. It creates a timestamp here in your file. It updates a timestamp in your source code that and it's going to do that when I click a button. So I click a button, it's going to make a code change, and that code change is going to have hard coded into it the exact time when the code change happened. When this code gets compiled and it runs, so the minute it's running, I'm going to have the current time when it's running. So it's going to compare the time when the program is running with the time when the code change was made. And that's going to give me down to the millisecond how long it took for a code change basically from me to saving a file to that file being running, up and running in my container, in my cluster. So that's what we're measuring. That's the time we want to shrink down as much as possible. Okay, basic attempt. So this is the very simple Docker file, very simple basic setup with tilts. This is like the simplest possible thing you can do. And I was supposed to have a GIF here. There you go. So this is a screen capture, and it's going to take a few seconds. So what's happening here? I'm building an image, and to build an image, I have to download dependencies. So I download dependencies, I build the image, I push the image to a registry if I'm using remote building, and then I kubectl apply. Kubernetes is going to download that image from the registry. It's going to kill my old pod. It's going to start a new pod. It's going to do all the Kubernetes stuff that I don't need to bore you with. And then it's up and running. So it took 28 seconds locally. So that's like a decent chunk of time. Like, it's not terrible. If you have to work, if you have to live with a 30 seconds feedback loop, you can do it. But like, because we're not using CI, that's the biggest time save of all. So 30 seconds, I mean, it's manageable. It's not terrible. But the problem is it doesn't feel instant, and instant is what we're looking for. So let's see what we can do here. This took, on average, from 3 different measurements. It took 23 seconds on a local cluster, 59 on the remote one. The reason for the discrepancy is because on the remote one, I have to push things up and down on the internet, and on the local cluster, I'm basically just copying stuff around inside the same computer. So one thing that I noticed is that downloading all of my dependencies on every code change makes 0 sense. So let's just vendor stuff and save ourselves the time. So attempt number 1, we're going to do vendoring. This is a diff between the between the Docker file before that I used before on the left and the new Docker file on the right. So what I'm doing here, I'm just saying, hey, copy a vendor directory. And of course, I had to generate the vendor directory. And then I'm telling the compiler, hey, don't download all that stuff. Just use the stuff from this folder. And this is going to be a bit faster. So let's see how long it takes. 13 seconds. Okay, that is not terrible, and that's a huge improvement, actually. So now we're down to 12 local and 44 remote, and that is 50% of the initial time local and 73% of the initial time remote. So that's a good improvement. Let's see if we can do better. What if, well, this is complicated. I'm just going to show it to you on the Docker file. So what if, instead of copying a vendor directory to my image every time I make a code change, what if I download all my dependencies into my image on a Docker layer above the layer where my source code lives? That means that whenever I change my source code, I don't need to change my dependencies. I don't need to download my dependencies again because they're already cached in my Docker image. So that's going to be faster than vendoring because it's less stuff to do. I don't need to copy a bunch of stuff around, right? But there's an issue, which I'm going to show you after the benchmark, actually. So here you can see that the stuff that I wanted to do is already cached. And it's going to take less time, hopefully, than it did before. And OK. So 11.9 and 39.6. So locally, that's a bit faster. Remotely, it took a bit longer. I don't really know why. So usually wait, took longer? No, it was faster on both. Yeah, never mind. I'm sleepy. So it was an improvement on both, modest improvement. Usually, I would take this improvement and just leave it there. But my problem with layer caching is that if I change one dependency, I invalidate the whole layer, and I need to download all the dependencies again. If I'm vendoring and I change one dependency, that's all the changes. So if I have 1 GB of dependencies, with this layer caching, I'm going to invalidate the layer. I need to download the whole gigabyte of dependencies again. And if I have a gigabyte of dependencies and I'm vendoring and I change something, the thing that I changed is the only thing that I have to change. So that's why personally I don't use layer caching. And yeah, so the person who told me about layer caching was Dave Cheney. And I know of one project where people were using this, where he worked on, and it was successful. And I actually am dying to ask him why they chose that instead of vendoring. Probably because it was Kubernetes stuff, and Kubernetes stuff is really huge. But anyway, I'm going to ask him later. So point being, if this is a better use case for you than vendoring, you probably know it already. And if you don't, then it's not. And then just use vendoring. Okay, so how to improve next? If you Google how to improve my Go binary something something, you're going to find 100 billion results about removing debugging artifacts. So let's do that and see what happens. And if you don't know what debugging artifacts are, if you ever use a debugger like Delve for Go or basically GDB for everything else, then you know you need some information to be able to use those. And they are, the debugging artifacts. So they take actually a huge amount of space in your binary, and you can just remove them by telling the compiler here, hey, don't do the debugging stuff. It's pretty simple. The file size diminishes a lot. So went from 14 megabytes to 11, and I'm going to talk a little bit more about this size difference in a few minutes, because it's going to make more sense then. But for now, just know that it's a smaller file, and that's going to be a little bit faster. By the way, I didn't talk about what's on the screen. This is the tilt interface. So here are all my services, and these are the logs. So this shows me like the status of the service, when it's rebuilding or not. I can manually rebuild with the thing here. And then when something goes wrong, I get an alert to show me what the error is. So it's pretty nifty. But moving on. So 10.5 with a local cluster, 33.9 with a remote cluster. That's another modest improvement, and this is an improvement I'm going to keep. You just have to keep in mind that when you need to use a debugger, you need to include the debugging stuff, or you're going to have a very difficult time. So that's something to keep in mind. But since we're not doing, using actually debugging tools most of the time, I can just leave it off by default. So the file reduction was significant, and I'm going to talk more about it in a few minutes. Let's move on. Something else that Go is good with is the Go compiler cache is extremely impressive and extremely effective. And right now we have no compiler cache because we're creating a new image on every time, compiling once with that image, which generates a compiler cache, and then we're trashing the image when a new code change comes along. So is there a way to keep the compiler cache? Let's see. So this is just a little benchmark showing you that without a compiler cache, my service takes 4 seconds to build, and with a compiler cache, it takes 11 something there, basically nothing. So that's a lot faster. And the way to apply this is to just tell the compiler, hey, I have a Go cache, and here's where it is. So I'm going to show you the benchmark, and then I'm going to complain a lot. And let's see, it's going to be a bit faster. So 9.4. So 7.7 average local, 50 remote. So remotely it actually took more time. So we need to talk about what's going on here. The compiler cache is a huge number of very tiny files. Depending on the cluster you're using, even locally, that's going to take longer. So for example, Minikube has more issues with I/O than Microcates. So with Microcates, it's actually faster. With Minikube, it takes longer because of all the I/O. Remotely, it also takes longer because it's a ton of files that it needs to copy around that it didn't need to before. Also, there is a complexity issue. So if you're building an image, if you're compiling an app locally, you get a cluster. And then you try, sorry, my words are bad. If you're compiling some code locally, Go builds a compiler cache locally. And then you think, oh, that cache is probably going to work inside the image. But maybe you have a slightly different build of the compiler locally and in the image, and then the cache is not compatible. So in this case, I had to create an image, compile stuff in the image, extract the cache from the image into localhost. I capped that cache on localhost. When I had to rebuild the image, I popped that cache back into the new image. So I assume this didn't make much sense, this explanation, and the reason is because it's really complicated, and the complexity cost is a pain in the butt. And I didn't even try to automate some of those things because it was just like, okay, this is too complicated. Let's just skip this. But the point stands that compiler cache makes things a lot faster. So is there a way to keep a compiler cache without having to move a compiler cache around? And yes, there is. So here's what we're going to do next. We're going to have a container that is permanently running. So we're not going to rebuild containers anymore. We're just going to build a container once and leave it there. Whenever I make a code change, I'm going to update the code that is inside my container. I'm just going to diff the code. So like rsync the changes, basically. And then I'm going to recompile inside the container. So the first compilation inside the container is not going to have a compiler cache. Subsequent ones will, and they're going to be a lot faster. So that's what we're going for now. So I'm going to need a thing called live update, because instead of killing the container and building a new one on every code change, now we're going to leave the container there and just update little bits and bobs, little bits and changes of code when they happen. So live update is another function in Tilt. And by the way, all of these functions in my Tilt files are built into Tilt. You don't have to write them. So again, this screen on the left side, I have my previous Tilt file. On the right side, I have my new one. So this looks a bit full of stuff on the screen, but it's actually simpler than it appears. So what's happening now is I'm live updating the glitch directory from localhost with the glitch to the glitch directory in my container. I'm just making sure that whenever I change something locally, that gets reflected on the container. And then I'm going to have this compile script. Yeah, let's get to the compile script in a bit. So in the container, now I'm going to have this tool called enter. And what this does is it watches files for code changes. So whenever a Go file changes inside my container, enter is going to rerun my compile script. So I make a change locally, that gets synced to the container, that gets detected by enter, and then that gets recompiled inside the container. So let's see how long it takes, and it's going to be pretty fast. So boom, we are done. How long did it take now? 2 seconds here, 2.5 seconds there. So the promise that I made when I showed you the tweet in the beginning, there it is. If this were a live talk, I would say, can I have some applause, please? So 2.0 and 2.5, huge, massive improvement. If you're wondering why it's so much faster, especially remotely, it's because before we had to build an image, blah, 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 and then push an image to a container, download the image to the cluster, and reschedule, redo all the Kubernetes stuff. That's what we did before. What we do now is, hey, here's 2 kilobytes of source code that changed. Done. And you just recompile in the container and done. So that's why it's so much faster. This has issues though. It's very fast, but it's not perfect. So if you have 50 services, you are not giving much CPU and much memory to any of them. You're keeping them very tiny. And if you don't have enough CPU and memory, you can't compile, or you can't compile effectively. So we're going to look at that next. Also, because this requires you to have all the tooling to do the compilation inside the container, these are probably not the images you want to use in production. Because usually in production, you want a very tiny image with no tooling in it, just an executable. So we're going to talk about that also, but later. So let's say I have half the CPU, and I try to do the same thing. So here's, half the CPU. And locally, it took twice as long. And on my remote cluster, I decided, you know what, let's do 1/10 of the time. And then it took basically forever again. So if you have enough horsepower, let's say, this method is really fast and really simple, and I love it. If you don't, that's an issue. So how else can we improve it? So what if instead of syncing the source code into the container and compiling in the container, what if I compile locally on my laptop? Because even if you're using Windows or Mac, you can compile it for Linux with Go and then just ship the Go binary. So instead of syncing the source code and compiling in the container, what if I just compile locally and sync the resulting binary? So that's what we're going to try next. One issue though, when you compile on your local machine, you're going to use the standard Unix C library. And if you're using an Alpine container that uses a different C library, they're not compatible. You're going to get a cryptic error message. You're not going to know what to do for hours. And so I'm just telling you up front, when this happens, and it is going to happen, what you need is to make sure that you have a static binary. And you do that by saying cgo enabled 0. So no more dynamically linked C libraries. Now, I'm going to change something else. So because I'm compiling locally, I'm just going to make sure that when I update my source code file with the new timestamp for the benchmark, I'm already going to compile on the same step. And this is what my compiled script is going to look like locally right now. So this is not best practices. If you're going to do this for real, you're not going to implement it exactly like this. I'm making it like this here just for simplicity. So what's going to change? And again, this screen looks very scary, but it's just a diff of 2 files, one on each side. So the difference is that before I was syncing a whole directory with the container, and now I'm just syncing one binary. So whenever I recompile, I create a new binary. That binary gets synced into the container, and now enter the thing that watches my container for code changes. Instead of monitoring my source code files, it's just going to monitor that binary. When the binary changes, rerun it. That's it. Also, you can see that I'm not using a Go Alpine container anymore. I'm just using an Alpine container. So this is something you could use in production straight away. So in this case, we have one image that you can use for development, and then you can just take that image and use in production, and that is great. So here's what it looks like. And ta-da, boom, done. Okay. So average 1.8 locally and 9.9 remotely. So we're going to talk about that. And I have no idea how I'm doing on time, actually. All right, so massive improvement. This is the absolute fastest time you are getting if you're using a local cluster. Like I don't think you can make it faster than this, maybe with a Scratch container, but that involves extra headaches that might consume more time. Remotely, though, here's the thing. Before, I had to sync like a few kilobytes of source code at the most. Now I have to sync a binary, and Go binaries are pretty big, so like in tens of megabytes. So a few kilobytes, tens of megabytes. This is a problem. That's why this is taking so long here. So let's see if we can address the binary size by wasting time with something else that's going to save us time here. Okay, so a lot of people think that, oh, the code that came out of the binary, the code that came out of the compiler, it's machine code. It's already, super compressed. I can't zip it. And then other people are thinking, like, yeah, but and also like when you send packets via TCP, they get gun zipped. I think I don't know. I studied networks 20 years ago. They get gun zipped. So like whatever you're sending up and down the network, it's already compressed as much as you can. And no, everyone's wrong. I'm just putting it out there. So Ultimate Packer for executables. You can find it on GitHub. It's a tool, and it takes a binary and compresses it. It can compress a lot, and then it takes a lot of time because compressing is a very expensive operation, or it can compress a little bit and it's faster. And let's take a look at how this works. So I'm doing the same thing I did before, compile locally, sync the binary. And it took longer on localhost. And by the way, all of these recordings are on localhost, not remote. Important thing is now I have 40% of the size that I used to. So my binary is now 40% of its initial size because I compressed it. And look at that. The time for the remote cluster went down very significantly. So let's get to the table here. Using file compressing for a remote cluster makes it a lot faster because now I'm sending a lot less data through the network. But there's a caveat. You need to balance how much computing power you have in your computer with how fast your internet is. Because if you have a lot of compute and very bad internet, you might want to adjust UPX to compress it harder. So you have a lot of CPU anyway, so compressing is going to be pretty fast. And then it's going to be faster. But if your internet is insanely fast and you're developing on, I don't know, let's say a 2010 MacBook Air or something, then you might want to compress very little and just send it down the network. Or even don't compress it if your internet is that fast. And this is going to be time effective anyway. For localhost, when I'm using a local cluster, it doesn't make sense to compress things because compressing it takes longer than just copying the thing inside your computer anyway. So final score. Let's now talk about the big picture here. If you have enough compute power on your remote cluster, like if you're using a remote cluster and you have enough compute power, just sync the source code. And that's going to be the fastest thing you can do. Issue is that image is not going to be the same image you use in production. So that's something to think about. If you're using a local cluster, just build locally. Hands down, that's the fastest. Of course, I'm talking about Go. For different languages, you're going to do different things. So if you're using Python or Node, for example, or I don't know, Ruby, you just always want to hot reload the source code. End of discussion. That's it. But for Go, building locally is going to be the fastest. And yeah, there's a lot of discussion we could have about, what's the best thing to do for each environment. But we don't have a lot of time here. So one other thing I wanted to say, here when I compressed my file and saved a couple of megabytes and it made things so much faster, that's why removing debugging information is so important, because those 3 megabytes that I gained here, they make a huge difference down the line. So just so you know. 2 things we didn't explore. Actually, one thing we didn't explore is Scratch containers. Mostly because they're probably faster, but they're also a headache without the little things that you have to pay attention to, and I was feeling lazy. So if you want to test them and show me the results, I will be very happy. And also, if you want to go further down this road and study more about these things, check out Jerome Petazzoni's blog series, Reducing Image Size. And that's a fantastic read as well. And it talks about a bunch of other languages too, so that's really cool. Thank you, and please reach out, tweet, and yeah, that's it. So do I stop sharing my screen now?
Thank you very much for the great talk. There is one question, but we are pretty short on time. So I will send you the question and you feel free to tweet that. And I will invite everybody who wants to ask you more questions to tweet at you. And also to include the conference hashtag so you can be part of the raffle for the 3 JetBrains licenses. And the schedule is in the link below here in the streaming. And please follow us on Twitter, GoRemoteFest. And if you want to hear the background story for this background, you'll have to tweet at Ellen as well. So thank you again very much.
There's a video. You can go to my Twitter profile and see the video where those pictures come from.
Maybe you can retweet that with a conference hashtag and this will be retweeted.
Yeah. Thanks a bunch, Natalie.